Hi there! Welcome at Module 1, Microbiome Research and Causality. People have the innate ability to recognize patterns and make connections in order to understand the world around them. This is why people often make mistakes when it comes to coincidence and correlation and causality. With causality we mean that A influences B, while a correlation only indicates that A and B show a linear relationship. From analysis of huge amounts of data, often called big data, we sometimes find striking correlations. For example, there is a strong correlation between the amount of people who died by drowning in Europe and the number of popsicles that were sold in the same year. So can we conclude that eating popsicles is dangerous? Well, maybe for your body weight, but you will probably not drown by it. These two observations actually have nothing in common. It is more likely that there is a third factor involved that has something to do with eating popsicles and drowning. In this case, it is the weather. During a hot summer, more people are swimming, and thereby the number of drownings increases and people also eat more popsicles. In line with this, there also seems to be a correlation between the numbers of deaths by drowning and the amount of times that Nicolas Cage appeared in a movie. For this example, it is less easy to find an explanation for these two events to show the same trend over the course of 10 years. What do you think that in this case the third explanatory factor might be? Or is this correlation sheer a coincidence? The one who seeks finds. When you search hard enough, you will find the most ridiculous correlations. By making use of the endless sources of information from the internet, this has become way more easy. If we analyze these large data sets with all their parameters, there is a high chance that we will find a correlation, while in fact these parameters show the same pattern, just by a coincidence. In the case of Nicolas Cage, you will have this gut feeling that this doesn't make sense. However, intuition is not the way to go when we talk about complex data. Biologists and clinicians all try to find correlations between the gut microbiota and health outcomes. Most often, these studies do not show a causal link. For example, people who suffer from a disease often have used medication for a long time, and people with obesity have been eating unhealthy for a long time. These factors will also influence the onset of the disease and the gut microbiota composition. Moreover, other factors, such as genetic background and country of origin, will also play a role in the gut microbiome composition and the chance of developing a certain disease. The main challenge is to figure out the changes in the gut microbiome actually play a role in disease. Can we think of an explanation for the fact that in a data set of thousands of bacteria, some of them show a correlation with the disease, or is this based on sheer coincidence? From correlation to cause and effect. A rather good example of a causal relationship between gut microbiome composition and the development of a disease is a fecal microbiota transplantation. This was done in patients with a Clostridium difficile infection. This microorganism is only able to thrive in people with disturbances in its gut microbiota. Moreover, a fecal microbiota transplant of a healthy gut microbiome composition can restore the balance and get rid of the Clostridium difficile. We can also find examples of novel health-promoting microorganisms. The bacterium Akkermansia muciniphylla is more abundant in healthy people and often absent or low abundant in humans and mice with obesity. Researchers have found that there is a relationship between this bacterium and the metabolic health of the host. This means that when you feed mice Akkermansia muciniphylla, it has a positive effect on weight balance and metabolic health. An ongoing clinical trial with pre-diabetic patients still has to confirm these positive effects on metabolic health in humans. Luckily, we have approaches available that we can use to find causative relationships between the gut microbiome and health. For example, germ-free mice. Those are mice that were never in contact with microbes. If we expose these mice to microorganisms, we can test the effect of the specific bacteria on, for example, metabolism, digestion, or immune responses. Of course, these models don't give us a decisive answer on the effectivity of a potential treatment in which we influence the gut microbiome. Therefore, we will always need clinical trials in an appropriate group of patients. I hope that researchers will continue their good work investigating the gut microbiome, because by doing so we might benefit from personalized treatments against diseases while taking into account the differences in our microbiome.